many other things like pack sticks we talked about. They're on the slides, but I didn't, unless I cut them out, I didn't get to them in class. Things like distils. Or, oh, I know we talked about this one. Tin Man. I was telling my daughter how clever I thought it was for saying, what do you think a gene that caused you not to have eyes would be called? Eyeless. What do you think a gene that caused you not to have a heart would be called? And people immediately chimed in with heartless. It's Tin Man.
So, what's a homeotic mutation?
Oh, very good. So, we didn't quite get to that, just to the edge of it. So, if you have a mutation that causes confusion about segment identity, then you might end up with something, let's say you have segment here that makes antennae, segment here that makes mouth parts, big teeth, segment here that has a leg, segment here that has a leg, segment here that has a leg. If you have a mutation in one of these genes that's telling you where you are front to back, one of the segments might be confused about what kind of appendage it's supposed to make. So we talked about this idea of developmental cascade. If the Hox gene is going to start with developmental cascade, it's going to give you the right appendage, but you get the wrong Hox gene expression. Then you might end up with, and this is the example, one of the examples we had, a leg, foot under here, where the antennae is supposed to be. So you didn't change anything about the genes about how you make legs and antennae, but you just changed one of these genes that tells you what segment you're on. So this critter thought that it was supposed to be making a leg here, when in fact it's supposed to be making an antenna. And people have known about that for, well, since 1896. Batesian mimicry fame describes something like this. And one of the things that's really interesting about it is it shows that, boy, there must be some kinds of underlying rules for development. It's not a very complicated and very specific, oh, this is how you make a leg on this segment. It's, you've got these master control genes that start development, maybe the same genes in different places, but they may differ in ways that describe why this would be an antenna versus this would be a leg. So it's not like you just get a big gamish when you have something expressed wrong. You just get a leg where an antenna is supposed to be your vice versa. And let's see, there's, in the movie there's talk about eyes being formed in unusual places or different initiators for development of an eye. So from a fruit fly to a screaming mouse, actually I think it was the ultimate.
Why does total potency usually get lost?
Yeah, we had to be a little quick on that. But the main point is that every cell has all the information it needs to make anything. And it gradually, the range of things that it can form gets smaller and smaller and smaller. We probably wouldn't have gone much into the mechanism anyway, but methylation, genes get silenced later in development.
I wasn't sure if that meant like, why don't we have totipotent cells? Just period.
Oh, okay. Yeah, that wasn't what I was getting at, but that's a good question. So why aren't all of our cells totipotent? Would that be sweet? Any speculations people want to? Pardon? Yeah, my guess is probably a way to prevent chaos and tumors and cancers and all kinds of things. So you silence some genes as you're getting towards a target tissue, and then, yeah. No eyeballs on the elbow. Okay.
I just wanted to clarify the developmental cascade. Is that the signal cascade that determines cell type, or is there more to it than that?
Well, it could be both. So the question is the developmental cascade the signal cascade that determines cell type, or is it bigger than that? It is what determines cell type, a lot of it. So since everything has the same gene, there has to be something that tells this particular cell, say, be a liver cell. And what that is all these effects from whatever initiates next set of cells to the next set of cells, the environment eventually gets to say, you're supposed to be a liver, and we can turn off all these other genes. So there's that. There's also morphogenesis, which is production of organs, so it's beyond just the cell level. So if you give the wrong signal way upstream in the developmental cascade for making an appendage, you might make this a leg instead of an antenna. Or if you, and this is some of the classical embryology they did back in the 30s, if you cut off this little part of the developing embryo and stick it on the back of another embryo, you're going to get a whole new embryo developed, because those cells were going to start this cascade of signals that eventually give rise to a whole organism. Those both. So cellular thing, and it's a larger structure.
Move on here, it says, can you describe the relationship between relatively recently discovered homeodomain genes and the long-known phenomena of induction of developmental cascades?
Tony, do you want me to answer that?
Yes.
Okay, well, I will expand on what I just described, and that is when people did things like cut off the dorsal lip blastophore, the big E in embryology, and you stick it onto another embryo, that's enough to start development of a whole new embryo, not from those tissues, not from those cells, but from cells that are around it on that new embryo. And that's weird. So people said, boy, there must be something in those cells that's telling those other cells what to do, and then they tell other cells what to do, and so on and so on. So that's the developmental cascade. Does that make sense? But people had no idea exactly how that was happening. So when they realized that, oh, there are these homeodomain genes that are acting as transcription factors, now people started to understand the mechanism by which one population of cells can start this cascade to turn on genes in other cells, that turn on genes in other cells, and so on and so on. Is it echoey for you guys? Can you?
Yes.
Okay. I wonder if I can get them to carpet this room. I suspect not. We're in the floodplain, so it probably has to be.
So I have the Darwinian medicine. Can you explain how compensatory strains usually, mutations might influence loss of resistance in the absence of antibiotics? Does that mean
Jake, you know?
that? No.
I think from what I read in the book, it's that it's costly for bacteria to become resistant to antibiotics. So when you take away antibiotics, it's favorable to get rid of that resistance, and that happens through kind of like back mutations or compensatory mutations, and it brings back their original fitness to how it was before.
So what you said was right, except for how we use compensatory.
So I would in context.
So, Charlie, yes.
Yeah, so compensatory is you're compensating for something. So what you said, like antibiotic resistance, it kind of changes something that was really good in the bacteria cell. So it's already added to adaptive peak. Changing this lowers it on the adaptive peak. However, compensatory mutations will be like, oh, well, I'm actually going to, that doesn't actually do this, but there's another mutation that says, that changes it again. It's still resistant, but there's another kind of mutation over in this area, and now it's actually back up at that adaptive peak. So now it's on the same fitness level, both in, or like it's in the same fitness level without the antibiotics as the one that is resistant. So it's like, it has more fitness in antibiotics, but it has the same amount of fitness because of this compensatory mutation that changes something that is doing. It's kind of hard to explain.
Yeah, I think I'm having a hard time with compensatory.
So take a crack at it?
Yes.
So if you have resistance to antibiotics, that usually comes at a cost.
Right.
Because antibiotics usually target some fundamental physiological process, so you have to do things in a clunky way to deal with the antibiotics.
Right.
In that circumstance, their selection for, in the presence of antibiotics, getting ever more efficient at dealing with the presence of antibiotics. And you might have mutations that make you just as good at doing what the original process was in the presence of antibiotics, or even better, than in the absence of antibiotics. So there's the sense that well, you have all these antibiotics and you develop resistance, or you just stop using the antibiotics and everything's going to go back again. That may be true, and it often is, but it may also be the case that if you always have antibiotics out there, organisms are going to figure out ways to deal with those antibiotics and be no worse off than if they weren't resistant.
That's a Lacey situation.
So is everybody okay on the idea of compensatory mutations?
Can you explain pattern information?
Yeah. I don't think I said much in class about it, but pattern formation just is, I'll give you an example. When people, these old embryologists, were looking at lymph development, say, they would see this undifferentiated nub of tissue, and then gradually bones would start to appear in very characteristic ways, very characteristic places. There'd be a front, there'd be a back. So all it is making a pattern out of something that didn't really have any organization to it. So the other phrase would be morphogenesis, a development of form. And as is usually the case in science, you look for the patterns, and if you repeatedly see limbs developing the same way, then you want to know what's the underlying mechanism for that.
Can you give a definition to ontology?
Ontology.
Yes.
Ontology or ontogeny?
Ontogeny.
Ontogeny, okay. So ontogeny is essentially the pattern of development. So when you say ontogeny recapitulates phylogeny, then you're saying that what you see in development of organisms essentially reproduces what you saw in evolution of organisms. That's not exactly true, but there's some information in development. So ontogeny is just a pattern of development.
Sorry, I missed that. Can you say that again?
Sure. So the last part about ontogeny recapitulates phylogeny?
Right after, yeah, right after that.
Okay. So when you say ontogeny recapitulates phylogeny, you're saying the pattern of development, that is ontogeny, follows more or less the same course as the evolution of those organisms. And I'll give you an example. Early in development, you had a notochord, which is a long stiffening rod that is more or less where your backbone is now. You pretty much lost all of that in development. So during ontogeny, you've gone from having a notochord to no longer having one. If you go back 540 million years, you would see chordated ancestors with a nice big notochord, and in the evolution of mammals or vertebrates, that gets smaller and smaller. So, in a very general way, that replaces that.
Can you explain a little bit about the genetic bilateral ancestor, how we can take the even with one of the three answers?
Sure, I'll do that. If I'm getting two calls in rapid succession, probably would. Really? Really?
Genetic bilateral.
Can you hear me? All right, I guess you'll have to try again. So here's what we're trying to do. So we've got bilaterally symmetrical animals. And they have this huge range of complexity, huge range of shapes. It includes worms and flies and mammals and all kinds of things. So we might be interested in, well, where did this all come from? So what did the common ancestor of all bilaterally symmetrical animals look like? So the usual thing we would do with that kind